Hi, I'm Sanjeev. We're in the Willis Annex Laser Lab. This is PJ. PJ, do you want to give an introduction of yourself and what you do here?
Yeah, sure. Well, my name's PJ, and I'm one of Tracy's postdocs, and I'm currently working on this rig over here, which is called the Myocardial Bridging Rig.
Cool. Myocardial bridging, wow, that's a lot. Yeah, what's that?
Yeah, so myocardial bridging is an inborn condition, so it's something you're born with, and it's actually quite common as well. It occurs in about 19% of people, from what a recent study has shown. And it's basically a condition wherein the coronary arteries, which supply blood to the heart, pass through the heart muscle itself, as opposed to lying on top of the surface of the heart, which is what would normally be the case. So what can result is that every time the heart contracts, it causes the artery to be compressed, because the artery is surrounded on all sides by the heart muscle.
Okay. So is that the main motivation, to see what the contraction is doing to the artery? Or?
Yeah, exactly. So we want to perform a series of flow visualization studies using this rig to try and get an understanding of what's happening to the flow, because the condition has been linked with a series of diseases, such as deprived blood flow to the heart muscle, and also irregular heartbeats as well. And at its worst, in the worst case, it's been linked with sudden cardiac death as well.
Okay, yeah, intense,
So that's the main motivation. The other motivation is because it's really difficult to visualize this stuff in an actual person. So the only real option we have to properly see what happens due to the contraction of the heart muscle on the arteries is to perform it in a lab using this in vitro rig.
Okay. So yeah, you touched on this in vitro rig, which is a very complex system. Do you want to show us different components and explain?
Yeah, sure. So I may have mentioned earlier that we're interested in looking at the pressure and flow data within the artery.
Yes, you did.
So one of the things we're using to measure the pressure is this. It's a pressure wire, which was modified by Joseph, who's one of Tracy's PhD students. And what we can do is we can feed this pressure wire anywhere through the artery. And the artery is right over there, by the way.
Yeah.
And we can measure the pressure anywhere upstream and downstream of where the heart muscle causes the artery to contract.
I guess because you see disturbances on both sides, not only at the
side. Exactly.
Okay, so that's the pressure side as well. So that what's this big arm that you got? So I guess that's assuming is what the heart does, but do you want to?
Yeah, so this is designed by Josh, one of Tracy's previous PhD students. And basically it moves up and down. I can show you how it works, actually.
Cool.
So,
that'll be... Yeah, okay.
So as you can see, it's moving up and down and causing the artery to compress at the moment. So this is just replicating what the heart does to the arteries.
Okay, that's really cool. Yeah. Sorry, going back, the pressure data, it's pressure wire, that's from the clinic. I've heard of that in the clinic as well.
Yeah, so this pressure wire was actually taken directly from a clinical pressure wire and modified using Joseph's software so that we can use it in the lab.
Okay, cool. So you've got software controlling the pressure wire, and I guess this the rig as well. Okay, and you've got the artery sitting in a bath. Why is that?
The bath was there so that we can fill the tank up with glycerol water, which is used to closely match the refractive index with the artery that we see over here. Yeah. So this artery is made out of silicon, which is made by mixing these two components over here. So this is polydimethyl siloxane, or PDMS. So by combining the base with the curing agent, we can get arteries of varying stiffnesses. Okay. So this one's quite flexible, and that was designed to simulate a healthy artery. Okay. However, if we want to simulate a more diseased artery and make it stiffer, we just have to add a bit more curing agent.
Right. Okay.
So the bath was created so that we can cause these arteries to disappear, essentially. So that.
Why would you want that?
That's so that we can shine a laser through the tank, and so that we can pass some fluorescent particles through the artery itself. Okay. And by doing so, we can visualize exactly what's happening to those particles as they're going through the artery, which is only possible because everything's transparent.
Right, okay, yeah. And you don't see, there's no contortion or there's no obstruction.
Exactly, so the laser just goes straight up through the artery instead of being distorted.
Okay. But like, this definitely is bigger than a normal artery. I guess you need to scale it up to see more resolution. But what does that come with? Like, what does that come with? You probably need to change the conditions.
Yeah, that's right. So, in order to exactly replicate what would happen in a life-sized artery, which is about 3.5 millimeters in diameter.
Okay.
So this one's scaled up 4 times so that it's 15 mils in diameter.
Right.
And in order to exactly match what's happening to the fluid dynamics, we would have to make adjustments to the time scale of the. We have to adjust the period over which the pulses are generated by our pump.
Yeah.
And we also have to adjust the density and viscosity of the fluid as well.
Okay. Both Wormsley's number and Reynolds number.
Yeah, that's
I guess
right.
the scaling. Yeah.
So by matching those two non-dimensional numbers, we can achieve the same flow characteristics.
Cool. You mentioned a pulse, so it's not just steady flow. You're varying the flow as well, is that right?
That's courtesy of this big pump over here, which was designed by Vince, one of our machinists.
Right. Yeah.
And so it's a piston pump, and it's capable of generating physiological flows.
Okay. Okay. And it varies the pressure, I guess, as well. Yeah.
Yes, that's right. So I can show you what that looks like now, if you want.
Cool.
So I'll just set it to reset.
Right. Okay. It's pushed up.
And as you can see, it's causing the pressure to change.
Yeah. Yeah. No, that's pretty cool. Yeah. So there's another component that has been controlled electrically, I guess. So was this problem given to you from the clinic, or was it the engineers that tried to fix the problem?
We're actually performing this problem. We're learning about this problem in conjunction with Concord Hospital, who have done extensive research into myocardial bridging as well.
Okay.
And they've actually supplied us with pressure data from patients who have this condition. Okay. And so they've obtained this data from patients with mild and severe bridges, from which we can use to validate our experimental model. Okay.
Okay. So yeah, actual physiological data for validation, I guess. This is a very complex system. Do you want to outline some challenges you face with this?
So one of the main challenge which I'm currently trying to overcome is to try and make sure that all of these components can work together so that everything's synchronized. Because what would happen in the ideal case is that the pump would be synchronized with the myocardial bridging rig, as well as the laser, so that we can get the pulses occurring at exactly the right time whilst the bridging takes place.
Right, okay. Yeah, so like 3 components that you need to control, I guess, with one trigger, I guess. Yeah. No, that's intense. Where do you see this research developing into or going forward from here?
Well, in the short term, we'll be using this model, this experimental model, to validate one of Jesse's computational models. Jesse's one of Tracy's PhD students. So she's looking at myocardial bridging, but from a computational point of view.
Okay.
But the problem is that we don't really have any clinical. Well, it's not really possible to obtain the flow data in any decent resolution in the clinic. So that's what we'll be using this rig for in the short term, to try and validate Jesse's model. And from that, she can hopefully create more complex bridging models with physiological arteries.
Right, so yeah, very interesting. A prevalent condition that you're trying to match up to the physiological condition to as much as possible with this complex setup. Thanks a lot for showing us all these components.
Yeah, no worries.